Okay, very good. So excellent. So we have Jeremy Gamble talking about Witten's approach to the Morse inequalities. Jeremy, please.
Right. So yeah, I'm gonna talk about the Witten approach to the Morse inequalities today. Um, the talk will look something like this. I'm just gonna introduce a little bit of Morse theory for those of you who've never seen anything from Morse theory before. Then the bulk of the talk will be kind of sketching out the proof of the Morse inequalities using Witten's approach. It will be pretty sketchy as he uses results from, so I'm following a proof from John Rowe's book, Elliptic Operators Topology and Asymptotic Methods, the one we are using for the course. And he uses a lot of results from throughout the book. You would need many hours of lectures to like kind of get everything you need. So it will be sketchy and hopefully just demonstrating the main ideas of how this kind of goes. There's kind of three main lemmas to break down the theorem into, and I'll discuss those each in turn. And then I'll briefly talk about some applications of these inequalities, you know, some ways to think about them and things like that. So let's start with some basic Morse theory. Okay, so the main idea of Morse theory is that if you take a good smooth function on a manifold, then you can get like lots of topological information about the manifold out of this function. So for example, if we consider the height function on the torus, you've got like a torus embedded in R3, and you know, this is just taking the Z coordinate. This is an example of a nice function that encodes some topological information. So to find the topological information, you look at the critical points of such a function, and it's easy to see just visually that the critical points are going to be here at the bottom, one in the middle where like the, you know, where the donut shape starts, and one here, and then one at the top. You can do this by just, you know, viewing it as a submanifold of R3 and then looking at where the tangent plane in the Z direction is flat, which is obviously on those 4 points. So you can consider these sublevel sets and level sets. So these are just basically all the points in the manifold for which the function is below a certain value or equal to a certain value. And what you can kind of see is that every time you pass through a critical point, the topology of these level sets and sublevel sets changes. So you can see like when you come up here, it's like a circle, and then when you get these double circles when you cross over one of these middle ones for the level sets and so on. And this is kind of like one of the main ideas of Morse theory, is looking at these sorts of things. Okay. So let's talk about this a little more rigorously now. So a critical point of a Morse function is when the derivative is 0, as I was saying before. And we say a critical point is degenerate or non-degenerate if its Hessian is an invertible matrix at that critical point. And you can calculate all this stuff in charts, and basically because, you know, chart transition maps are diffeomorphisms and the chain rule and stuff like that, this all turns out to be coordinate independent definitions. So you can do this a little bit more coordinate independent, but I figured I might as well just show it in the way that most people have seen these things before. And we say that a smooth function f is a Morse function if all the critical points are non-degenerate. So in the previous slide here, the height function is an example of such a Morse function on the torus. Okay, and now we need a couple basic results from Morse theory. The first one is called the Morse lemma. And this basically says that the second order Taylor expansion for a Morse function around a critical point is perfect if you pick a suitable neighborhood. And the negative signs and positive signs here are associated to the number of negative and positives of the Hessian matrix. So alpha is the number of negative eigenvalues of the Hessian, and you know, the rest of them are the positive eigenvalues of the Hessian. And we call alpha the number of negative eigenvalues of the Hessian, the Morse index of f at the point P, or just the Morse index at P. Why we choose the negative one isn't, rather than like the positive eigenvalues, isn't super obvious, but we'll actually see this kind of come up explicitly in the proof of the Morse inequalities. It turns out that picking the negative ones is kind of the right tool for the job. And as a corollary to this lemma, it follows that the critical points of a Morse function are all isolated, because you can just compute the derivative of this thing and you can see that, around a neighborhood of the critical point, it doesn't vanish. And then it follows for a compact manifold that this only has finitely many critical points. And just to give you an idea, these Morse functions, they always exist. And in fact, the average function you pick off of a manifold will in general be Morse. They're dense and all smooth functions. So they're available in abundance. It's just a matter of choosing the right one for the job you want to get done, essentially. Okay, and I'll show the Morse inequalities really quick here, just so you have an idea of what we're trying to prove. So we take a smooth closed manifold and a Morse function. Then we get this system of inequalities where these betas are the Betti numbers, so the dimensions of the cohomology groups. And on the left-hand side here, we have these nus, which count the number of critical points with the associated Morse index. And the last one turns out to be an equality, and this is the Euler characteristic here. So I wasn't sure who originally proved these inequalities. I assume it was Morse himself, but I didn't end up finding, I didn't go through the old papers, so I didn't find an explicit reference. But the original proof, I believe, was done using like cellular homology and things like this. And the method we're going to use is kind of a more analytic, spectral geometry type proof, since it's a spectral geometry course. And the advantages to this proof, as far as I can tell, are that you kind of get to see what's happening a little bit more explicitly. And also you get a little bit of that relationship between the spectrum of like the Laplacian and in this case, it will be like a perturbed Laplacian, and the topology of the manifold. So it's kind of like another one of those spectral geometry correspondences we've been seeing throughout the course. One thing I do know is that there are proofs of these inequalities that take into account the torsion rank of your cohomology groups if you pick like if you take values in a ring where there can be torsion. And I wasn't sure if there's a way to prove that using this method, considering everything is kind of like deRham cohomology. So we're kind of missing out on that. Also, we're kind of restricted to compact manifolds, where I think you can prove Morse inequalities more generally as long as your Morse function has like a finite number of critical points. So there's some things that you don't get, but there's a lot of nice things you do get.
Excuse me, can
yes.
I ask you a question? What is mu here? Is it?
Oh, sorry, those are typos. Those should all be news. There's going to be muse appearing later for a different
And the last equation, is it equality or
yeah, it's equality. It's equality here, yeah.
Why you say it's a Morse inequality then?
Because all of these ones are inequalities, and this is the only one that's an equality. I mean, yeah, you're right. Technically, this one's an equality, but as like a set of relations or inequalities, I guess. Oops.
Okay. And another question: do you know what is the Morse-Smale complexes that one can attach to F?
I didn't dive too deep into Morse theory. I mostly stuck
Okay.
with the Witten approach. So no, I couldn't tell you about that. Sorry.
I believe this Morse-Mail complex appears also in Witten's approach when you look at the kind of eigenfunctions for this perturbed Laplacian. And I mean, so you have this you look at harmonic P forms under this perturbed with respect to perturbed Laplacian.
Oh,
And
maybe it does show up. Maybe it will show up in the talk, but
I
maybe
believe
I
it
know it
will
by a
show
different
up.
name.
I believe it will show up also. Yeah.
Okay. Okay. Yeah, maybe I just know it by a different name then, but we'll see, and hopefully your question will be answered by the end. But anyways, yeah, so the relation to spectral geometry here that we'll see is that we're going to be using kind of operators based on like the Laplacian to determine these inequalities. We're going to take the trace of like a certain function of the perturbed Laplacian, and it's going to give us these inequalities and a limit. So you it's kind of another one of those cases of you hearing some information about the manifold. In this case, you get these bounds on the dimension of the cohomology groups with this method. So that's how it's relating to spectral geometry. So now we'll get into this Witten approach. So we're going to start with this lemma on kind of like a prototype of the Morse inequalities. So if we just start with a regular old deRham complex, and we write d as d plus d star, and then obviously we have the Laplacian as usual, it's just d squared. And we pick a very nice, smooth, rapidly decaying function that satisfies this condition that 5, 0 is 1. We set the trace. So because we're choosing this to be smooth and rapidly decaying, this is a trace class operator now, and we can take the trace. This is going to be kind of like our new, except when we perturb this guy, we're going to have this as mu of s, and in the large S limit, this is going to be like those news, those numbers of critical points with Morse index j. So yeah, this is the first kind of main result on the way to the proof. It looks very similar to the Morse inequalities, except instead of being these critical point numbers, they're instead the trace of the Laplacian. One other thing I should mention here is that this lemma applies for any so-called Dirac complex where instead of omegas, you have Clifford bundles and like differential operators between them such that it makes a complex. So it's a slightly more general result than I write it here, but I kind of wanted to stick with the way we do things in the course, the kind of stuff we're familiar with, instead of talking about Dirac operators and Clifford algebras. So how do we prove this lemma? As with all of the things I'm going to talk about the proof of, I'm just going to kind of sketch it. So from the Hodge theorem, we know that the jth Betti number is just the dimension of the kernel of the Laplacian, the dimension of the harmonic J forms. Now what we do is we pick a second function phi that satisfies these three properties. So it's very similar to our first phi, it's just less than the previous phi. It satisfies the same property of being 0 or being 1 at 0. And then for every element of the spectrum of the Laplacian, for every single j, so on all j forms, we set it equal to 0, except for the case where lambda is equal to 0 itself, we don't do it there. And by doing this, essentially taking the trace of this guy, which is also a trace class operator, is going to compute the jth Betti number, just because we're going to sum over this thing over all the eigenvalues, and for all of them except for 0, it's going to be 0. And then for 0, it's going to be 1 for every time 0 appears in the spectrum. So we get the jth Betti number. And of course, just by linearity, we've got this guy here too, where if you take the difference of these guys, which is again going to be nice and trace class and satisfy all the properties we need to make this work, we get that the trace of phi minus phi tilde is mu j minus beta j. Okay, so now we have this function, and because it has a 0, because both phi and phi tilde of 0 is 1, we can, phi of 0 is going to be 1, so we can factor out this x here. And because it's a positive function and phi is greater than phi tilde, we can write it as the square of another function. And then we kind of write it in this form so that we can manipulate the trace in a good way and get those inequalities. So again, this is another trace class operator, as I said, and we can therefore write it down this way. Then what we do is we break up the Laplacian into this d star plus d star d, and we can get this equality here. Now, this equality here comes from looking at, it comes from using the cyclicity of trace when the operators inside the trace are both trace class, and also using the fact that both d and d star commute with the Laplacian, therefore they commute with any function of the Laplacian. So we're kind of using a couple things at once here, but basically you can just rearrange this so that one of the operators appears on the left, and then we swap d with psi of Laplacian squared. And that's why you get the j minus 1, because this is going to be acting on lower dimensional forms because of the swap with the d and the Laplacian. So basically just cyclicity of trace and the fact that those operators commute, you get this. And you can recursively do this and kind of use that old plus minus trick where you add 0 to one side of the equation to, so you kind of take this guy and you add the other part and subtract the other part. And because from the previous slide, we had that trace of this guy is mu j minus beta j, we get this kind of relationship on this side recursively. And we're pretty much almost finished proving the lemma at this point. Yeah, if we're looking at top forms, then because if we're looking at top forms, then because d is 0 on top forms, the trace of that guy's going to be 0, and you're going to get an equality. And I think I may have written this backwards. I think this should be d star d, not d star, so sorry for that. But yeah, because this will be acting on top forms, this whole thing will be 0 basically, and you'll get an equality. And if it's not, then you can write that operator as a star a, where a is a positive operator, and this guy's trace class as well. And then since you're taking a trace of a positive operator, you know it's greater than or equal to 0, and all those inequalities for the lower dimensional forms follow. So that's kind of how the first lemma goes. So we have our little prototype of the Morse inequalities now. Okay, is there any questions before I move on to the next part? Okay. So now what we're going to do is we're going to perturb this deRham complex. And the goal of this is going to be that, as I said before, let's just go back for a second here. We're going to have a system of inequalities where each of the mu's are going to depend on the parameter s in the perturbed deRham complex. And then what we're going to show in the large S limit, these mu's will tend to the nu's in the actual Morse inequalities. So now we're kind of working on constructing this appropriate perturbation so that this all works out nicely. Okay. So yeah, so now we have this perturbed deRham complex. So now we take a Morse function h in C infinity m, and we have these perturbed exterior derivatives and its associated adjoint, and then kind of this perturbed Dirac operator, which is like, you know, our square root of the Laplacian. So basically, we're just kind of conjugating d and d star by e to the sh, where s is our parameter that we're going to let go to infinity at the end. And it's just a result. You'll have to take for granted that when you square this guy, you basically get the Laplacian plus a term depending. This is just the norm of the gradient of h. And then this is an operator I don't really want to explain because it's not super relevant. But basically, this is just if you take an orthonormal frame and you you evaluate your Hessian at the orthonormal frame. These are Clifford left and right multiplication acting on this deRham complex. Now, obviously, the deRham complex is as a vector space isomorphic to the Clifford algebra of the same size, but the multiplication is different. They're different algebras. So you have this operator kind of acting by Clifford multiplication on the deRham complex. But anyways, it's not too important, but that's what the operator is anyways. So let me talk briefly about the motivation for this, I guess, because it kind of comes out of nowhere a little bit. So this was Witten's approach to the Morse inequalities that he wrote about in a paper in 1982. It's called Morse theory and supersymmetry. And I guess he was motivated by some ideas in supersymmetry to consider working with this sort of thing. So he kind of viewed, the deRham complex as like a super vector space, the even and odd parts being given by the even and odd degreed forms, and these d's and d star operators being kind of the supersymmetry operators. And then they were multiplied by appropriate factors by like I and things like this. And it turns out, I guess he says in his paper, I didn't go into a lot of detail because it was a bit over my head, but that this is related to like a supersymmetric quantum field theory, a free supersymmetric quantum field theory of some kind. And that's kind of what got him thinking about the Morse inequalities this way. And it's going to turn out later, we'll see that the harmonic oscillator is actually going to pop up in this guy in the proof. So it's kind of cool to see the harmonic oscillator, which is like the physicist tool for solving everything, even pop up here and proving the Morse inequalities. So that's just to give a little bit of motivation behind what's going on here, I guess. Okay, so we have this perturbed deRham complex and this perturbed Dirac operator, associated perturbed Laplacian. And you just kind of have to take it as a fact, because we can't prove it all, that any kind of thing you would want to do in standard elliptic operator theory is going to work with this ds. So, all your Sobolev stuff, your Garden inequality, you can do functional calculus. It's densely defined and self-adjoint and has discrete spectrum contained in the real numbers. All that kind of stuff applies to this operator, exactly what you would kind of expect to apply to this operator, ds. Okay. So now we're going to very quickly sketch the idea of the next lemma. This one is very technical, so I didn't want to go into too many details here. It's important for the proof in the end, but I don't think the proof of this lemma is so important. So anyways, you take phi to be a positive even Schwartz function with, again, the same condition, phi of 0 equals 1. This is to make sure that when you take phi of ds, it's going to be trace class. And also, because it's even, we're going to be able to apply lemma 1 here, because we can write phi as phi of ds squared because of the fact that it's even, basically. And then we have to fix a positive number. And this positive number we're fixing is kind of going to be the size of the neighborhood around each critical point of our Morse function. And then we're going to kind of take a really tiny neighborhood around these critical points and show that the contribution to the trace of 5ds is given by essentially what's exactly at the critical values, which will turn out to be those numbers we want in the Morse inequalities. So that's why we're doing all of this. Okay, so basically, lemma 2 says that the kernel associated with this operator, which does exist, there is a smooth kernel associated with 5ds. It tends to 0 uniformly on this tiny neighborhood, or outside of this tiny neighborhood around the critical point, so in the complement of the neighborhood. So basically, everywhere away from the critical points, this thing will rapidly go to 0 as s goes to infinity. So here's kind of a terrible picture I drew. So if we've got some surface here, and these, if say this is the critical points associated to the height function, right, like the torus, then the blue area is the area in which it's going to tend to 0 rapidly, and these are kind of our little row neighborhood around the critical points. Okay. Oh, this share screen thing is actually in my way. I can't even read what I wrote down. Oh, right. Okay, yeah. So basically, because we're outside the critical points, we can bound the gradient of h on the complement, and so we can get kind of a bound on this operator, like a lower bound on this operator ds, by bounding the gradient, since as we saw in one of these, in this previous result here, that we've got this positive contribution in the middle of ds. So we get this lower bound that way. And then through a very technical argument, I don't want to go too far into details for, we have to look at like differential equations for forms and Friedrich extension theorem and all kinds of stuff. But basically you can, because the eigenvalues of this guy aren't necessarily positive and this thing's densely defined, it's nice to have this operator A instead, which is defined on the whole Hilbert space and has positive eigenvalues since it's a positive operator. So basically we're just swapping out ds to A using some, general operator theory. It's not very important. And yeah, I don't want to talk too much about that. And then basically by this previous inequality, we can mess around with the Fourier transform and then prove that this equality is true. And then we can bound this operator here, A, by the same bound up here, just because it's equal everywhere it's defined, and it's defined densely. And then we get this kind of bound. This should be phi square root of A. We get this bound on this operator here because phi is Schwartz class and is rapidly decaying as s goes to infinity. We can bound it for each s, which implies that we just get a bound on this whole operator, which is good because these two things agree. And this thing tends to 0 as s goes to infinity. And then you can kind of clean this up a little bit and actually get a uniform estimate using some Sobolev space stuff. Again, I don't want to go into it too much because there's kind of a lot of details there and it's not super interesting, but yeah, you can improve this estimate. Okay, and I just wanted to talk really quickly about something interesting that's happening here. In the large S limit, this smooth kernel of this operator is becoming like increasingly concentrated at the critical points. And this is something that kind of pops up in a lot of areas of a lot of other areas of math, wherever you have critical points playing like a key role in whatever it is you're working on. So we have this Poincare-Hopf theorem, for example, where if you have a smooth vector field on a manifold, and the zeros of the vector field are isolated, the sum of the indexes of the vector field at each point is equal to this integral where we're using the Gauss-Bonnet theorem here. So you're computing this, this integral kind of by like a finite sum, which is kind of exactly what we're doing in for this kernel. In the end, we'll see that as s goes to infinity, the trace of this phi s guy will be given by just a finite sum. And in case you're wondering what the index of this is, it involves looking at like the degree map from algebraic topology. You look at like a disk around each critical point, and you look at the induced map between the boundary of the disk and the associated sphere, and then that has like a degree that's defined from algebraic topology. That's what the index is. It's not too important here. And then another example of this happening is the Dweester-Matt-Heckman formula, which I gave a talk on in the differential geometry course before, where we get this perfect stationary phase approximation for a Morse function and a manifold with like suitable conditions on it, basically. Again, the exact formula here isn't very important. What's cool is that, you know, this integral is getting computed by a sum, effectively, involving the critical points. And this thing seems to pop up whenever you get involved with critical points in Morse theory. You can always seem to approximate integrals perfectly by sums, which is cool. So I just wanted to mention that. Okay, so back to the proof. We've got our first two lemmas. The first one being that we've got these prototype inequalities, and the second one being that the smooth kernel of this operator 5ds decays really, really rapidly outside a small neighborhood around the critical points. So what we're going to do now is we're going to put a metric on M such that in like a small Morse neighborhood around each critical point, this thing is just the flat Euclidean metric. And then we just kind of, you know, piece it all together using a partition of unity. We don't really care what's happening outside of the critical points at all, because everything there is going to be tending to 0 anyways. And then we choose, again, we just choose this number sufficiently small so that this is flat here. Then we had this result before from a few slides ago that ds squared was given by the regular old Laplacian plus this kind of S order perturbation. And it turns out that if you look at this locally with this metric, it looks like this. This is the same as this here. So this H guy turns out to be this Z operator, and DH, I mean, you can just kind of compute this in your head by looking at the form of H here. So these are the eigenvalues of the Hessian, and they're popping up here as well. This should just be lambda, not lambda squared. That's a mistake. Sorry. I don't know how I didn't catch that. And this guy is like the commutator between taking interior product and exterior product with dxj. It's not super important, but what we notice here is this first part of LS is the harmonic oscillator operator, like the Hamiltonian for the quantum harmonic oscillator, or just regular harmonic oscillator. And then this is kind of like, you know, a little perturbation of it here with this Zj. And it turns out that this Zj actually commutes with LS. So you can diagonalize these guys simultaneously, and you can kind of easily compute the eigenvalues of this perturbed harmonic oscillator by looking at like what the eigenvalues are from the original harmonic oscillator. So this is the result. So, you know, we've got smooth, rapidly decaying eigenfunctions for this LS operator appearing here, this harmonic oscillator operator. And the eigenvalues are given by this formula here, where P sub j is a positive integer, and Q sub j can be plus or minus 1. So this is the part coming from the regular old harmonic oscillator. This might look familiar if you've ever seen the harmonic oscillator before, this first half of the formula. Obviously it's not as simple because, you know, we've got many derivatives. And then this is the part coming from the Z sub j operator. And you can kind of work this out pretty easily because the operators commute. So these are the eigenvalues, and it turns out that for K forms, because of that, because of the structure of this Zj, when this thing acts on K forms, exactly K of these Q sub j in any given eigenvalue must be equal to +1. And this is kind of where we see the critical points kind of first popping up. So, I mean, the Morse index of the critical points. So what this means is that this can be equal to 0 if and only if P sub j is equal to 0 and Q sub j take exactly the opposite signs of these lambda sub j's. And this is just equivalent to saying that K is equal to the Morse index at the point P. So that was a bit of a mouthful, but okay, you can look at this and you can see that this part's positive and this part's never going to outweigh this part here unless P is 0. That's pretty easy to see. And then the only way this part here can be 0, or the only way this whole sum can then be 0, is if Q sub j always takes the exact opposite signs of lambda sub j. Or maybe it needs to take the exact opposite sign so that every term here is negative, which means that you need to have this K be equal to the Morse index at the point P, because the number of lambdas that are negative is equal to the Morse index. So this is kind of where you're kind of seeing explicitly where the Morse index is popping up in this proof. And it pops up because of the harmonic oscillator, the perturbed harmonic oscillator. So here's lemma 3, and this is we're basically closing in on the end of the proof at this point. So this, if we remember, this L sub s is basically our d, the square root of L sub s is basically our ds, our Dirac operator. And it's saying that in the limit as s goes to infinity, that it takes the value 0 if k is not equal to m, and it takes the value 1 if k is equal to m. And we can actually just multiply it by any smooth function that's compactly supported and takes the value 1 at 0. So to prove this, you basically just apply the spectral mapping theorem to this function phi. And because it's rapidly decaying, any of the terms that depend on s basically just end up tending to 0 in the large S limit. So basically every term in this sum here is going to be 0 unless it's constant. And the only time it can be constant is when the eigenvalue is 0, which, as we said before, can only happen if k is equal to m by that previous argument. So basically you get this contribution of 1 for that single eigenvalue if it exists. And the rest of them just go away. And that gives you this first result where you don't consider the function b multiplying it. I'm not going to go into the details for computing this. If b is there, you have to like go and look at the the coefficients in the Hilbert space of this thing, and you have to show that this thing tends to 1 as s tends to infinity, and it's not particularly enlightening. It's just kind of a technical fact that we need to finish the proof. So I'm just going to skip over that part. But it's just some kind of simple functional analysis stuff. Okay, so now we can finally get the Morse inequalities. So now we're going to finish the proof off. Again, the same typo is made here. These should all be news, no mu's here. So this is just exactly what I've written before. So let's get to the proof of this now. So again, we we're taking the metric we described before, which is like flat around the Morse coordinates and then just patched together outside. And then we're taking our nice function phi, that phi of 0 is 1, and it makes the operator trace class. It's even, it has all the nice Fourier transform properties, blah, blah, blah. Okay, so yeah, by lemma 1, as I was saying, it's a general lemma that does apply to this perturbed deRham complex. We get those prototype inequalities for each s and the real numbers and associated Morse function h. So we've got like now a system of equalities for each s, and from these guys, we're going to get the actual Morse inequalities. So one thing you can see right away is that beta doesn't depend on s at all. You can just use this map to go between the deRham cohomology, the regular deRham cohomology, and then the deRham cohomology depending on h and s. And it's not very hard to see that it's a nice isomorphism, which means that these numbers are the same. This is just, you know, one chunk of it. If you have a form that's exact in the sense of ds, then you can write it this way, because remember ds was this conjugated operator. And then if we just write multiplied by e to the minus st, that tells us that omega itself is exact. And then, you know, everything else goes through similarly, which shows that these are isomorphic vector spaces. And so the Betti numbers are the same. Okay, so now we're almost on the proof. We've got the Betti numbers independent of S. Now we just need to show that in this large S limit that these mu sub j of S become the nu sub j. So to do this, we're going to take the trace of this operator we were kind of putting together and proving things about before. So basically we start by, so this is just by how we define mu sub j of S at the very beginning. This is just trace for a trace class operator. You can compute it this way. And then this is, there should be a limit as S goes to infinity here. Oh, no, actually, this is okay. We don't need the limit as S goes to infinity here because the limit's already been computed, and the terms outside of these neighborhoods around the critical points vanish because of that uniform tending to 0 that we had in lemma 2. And then we can rewrite this by choosing B to be a, you know, positive function compactly supported on these Morse neighborhoods and all that stuff. We can pick B that way, and then that's equal to this. We also need to take it to be 1 on these neighborhoods. So we kind of extend the support of the function just like a little bit outside of this neighborhood in order to make this work. And then now we're ready to apply lemma 3, because this is basically what we just had, right? Lemma 3 is we computed this guy to be 0 if k is not equal to n and 1 if k is equal to m. And that tells us that this is going to end up being the number of critical points with Morse index j, which is what we wanted to show, right? We've got this limit as mu sub j tends to infinity is equal to nu sub j. And we have to do a little bit more technical stuff technically to, this should be L sub s, again, sorry for the typo. We have to do some more technical stuff to basically say, okay, we can write this phi of ds as phi of L of s. And, you know, you just need some Sobolev theory and stuff like that to make it go through, but there's nothing very interesting going on there. So then you just identify everything happening on Rn with your little Morse neighborhoods, and then the result goes through. So that completes the proof, or at least the sketch of the proof. I know I omitted a lot of details, but there are a lot of details, trust me. This spans multiple, to get all the results you need, it spans like multiple chapters of this book. It's mostly focused on chapter 14 of Roe if you want to go take a look at this proof and some more of the details, but you will probably need to go look at chapter 9 and chapter 5 and 6 and 7. So for like all the little technical lemmas in Sobolev theory, elliptic operator theory, harmonic oscillator stuff. Yeah. Okay. So that concludes the proof. Are there any questions about the proof before and I'm almost finished here. I don't have the time. How am I on time? Okay, I'm almost finished anyways, but are there any questions about the proof?
Yeah, I just remember, I mean, in Witten's paper, he talks about this thing called quantum tunneling. I mean, for these Hamiltonians of Schrödinger operator. Do you see that also here? I mean, I suppose, I mean, we should see, I mean, he sees this kind of Morse inequalities as an aspect of quantum tunneling. I don't know how this, I cannot recall it now, but I remember there was mention of that. Yeah.
I don't remember the discussion about quantum tunneling in particular. I may have just missed it. I did kind of only skim his paper and I used Roe as a main reference.
Right.
There may be something like that in there. Yeah, but I can't say.
Yeah, sure. No, that's fine. I think this math literature completely gloss over the physical intuition behind the proofs. So.
Oh, definitely. Yeah. Yeah. The Roe book doesn't talk at all about the physics beyond the harmonic oscillator that kind of pops up. That aspect is really nice because you kind of see a little bit of the physical intuition, but in terms of thinking about the Morse inequalities from this quantum, supersymmetric quantum field theory, that's not obvious at all to me. And I'd probably have to poke around more and try to see how Witten thinks about this a little more to understand his how he got from A to B there.
Okay, fine. Yeah. That's good.
Okay, so applications. So this will just be really quick. I just wanted to give like a quick example and some quick results that just immediately follow from the Morse inequalities. So you get these weak Morse inequalities by just taking the sum of, two adjacent Morse inequalities, essentially the ones associated with K and K minus 1, and then you get a bound on the kth Betti number of M. So if you can find a Morse function which exhibits a certain number for nu sub k, then you have a bound on essentially the dimension of that associated cohomology group. So that's like kind of the hearing the cohomology group using the Laplacian you're getting out of this proof, I guess, if you want to view it from like kind of a spectral geometry perspective. And even more simply from this, the top Morse inequality, when k is equal to n, you have that the Euler characteristic is given by the alternating sums of these Morse indices, or number of critical points with these Morse indices. So as like a quick example, we can go back to the height function on the torus. You can parameterize it this way, where r is the radius of the smaller circle and big R is the radius of the bigger circle. And then in coordinates, you can write it down like this, and you can compute the Hessian. And it's pretty quick and easy to check that you get one critical point of index 2, 2 of -1, and 1 of 0. So by that alternating sum, the whole thing is equal to 0, and that's the Euler characteristic of the torus, which is what we expect. And you can find plenty of things in like other books and notes, things like Milner's book, where you can go and compute Euler characteristic of Klein bottle this way, or other spaces. And I don't know if I have any, I don't have any more examples written here, but there are some other things that this gets applied to. For example, I believe this was used in the proof that any manifold homotopic to an n sphere for n greater than or equal to 5 is homeomorphic to an n sphere. So the Morse inequalities come into play there. For example, they work in conjunction with this other theorem from Morse theory, the Reeb circle theorem, and a whole lot of work, a whole lot of other work. This is not an easy theorem, a whole lot of other work as well. But yeah, they pop up a lot in Morse theory for kind of distinguishing spaces, which is what you'd expect because they bound cohomology groups. Yeah. Oh, and my references for this, as I said, were Rowe's book, mostly chapter 14, this paper by Ed Witten, Supersymmetry and Morse Theory, and Milner for a bit of some of the other basic Morse theory stuff, which is, it's a nice book. I didn't read too much of it, but it's a nice book from what I read. Yeah, so that's the end. Any questions?
I asked all my questions, I guess.
I have a maybe a silly question because it was a while ago. At one point you talk about phi. Sorry, now I don't remember even where it was. The point is you have this phi hat, which has this support within minus rho rho. So I guess it's where you introduce phi. Here, yeah.
Here it is.
Is that supposed to be phi hat or?
Yes, it's supposed to be phi hat. It's pretty easy to construct functions like this in general, since the Schwartz functions, so the Fourier transform is like an isomorphism in Schwartz functions, right? And any bounded function kind of in that and nice and smooth will kind of do the job. So it's easy to construct this guy. And basically, when I'm doing this part here, this technical part, I glossed over with phi of ds omega equal to phi of squared a of omega. You need to use the Fourier transform and go through some hoops essentially to really prove that this is equal to this. So that's why the Fourier transform was kind of popping up. And yeah, I think that's why you need the compact support as well. So the integral is nice.
So I guess the part that confuses me about this is like the heuristic or the trick I've always remembered is that if you have compact support or small support in Fourier space, you have wide support in regular space.
Sure.
But we also wanted our phi to be small. So
just rapidly decaying. It doesn't have to be
Right.
necessarily small. It just has to decay fast enough at infinity to make the operator trace class. And beyond that, it doesn't really matter too much.
Yeah.
Again, we wanted it to be even, but yeah.
I think it means we have the uncertainty, what is it, the uncertainty principle? That we can't have both phi and phi hat very concentrated in.
Yeah, I mean, that's true.
That's true, yeah.
We cannot have both phi and phi hat compact support, but you can have phi Schwartz and phi hat compact support. And the reason is that there's based on two facts. First of all, the Fourier transform sense Schwartz class to Schwartz class. That's one fact. It's a bijection, as James said. And also the fact that compact support functions are Schwartz class. So you can just apply inverse Fourier and then you get your function. Yeah.
Exactly.
But again, it's also true that, I mean, you cannot have both compact support.
Right. But yeah, I don't require, in fact, I don't require it to be a compact support, just the fast decay, right? So that the trace argument goes through as s goes to infinity. So the compact support, By the way,
that fact has a very nice, the fact that you cannot have both phi and phi hat compact support has a very nice proof. I mean, uses complex analysis, and it's very nice actually. So it's it's a nice application of Liouville's theorem and stuff like that. Anyhow, on complex analysis. Anyhow, so thanks so much, Jeremy. This was very good. Thank you. Let's thank Jeremy. I mean, are there any other questions or comments? So I will stop the video.